Thank you very much for everyone for coming to this talk. It's a great honor to receive Dr. Keshav Parry at the Universidad Tecnológica Nacional Regional Core. The presence of Dr. Parry in Argentina for this talk is possible thanks to the sponsorship of the IEEE Systems and Systems Society through its distinguished lecture program. Let me make a brief introduction of our speaker. Keshav Parry received a PhD degree from the University of California at Berkeley in 1988. He has been with the University of Minnesota, Minneapolis since 1988, where he is currently Distinguished McKnight University Professor and Edgar Johnson Professor of Electronic Communications in the Department of Electrical and Computer Engineering. His research addresses VLSI architecture design and implementation of signal processing systems, error control coders, and cryptography architectures. Dr. Parry has published over 600 papers and authored the textbook VLSI Digital Signal Processing Systems, Design and Implementation, which was published by Wiley in 1999. Dr. Parry is the recipient of numerous awards. He served as the editor-in-chief of the IEEE Transactions on Circuits and Systems, Part 1, during years 2004 and 2005. He was elected a Fellow of IEEE in 1996 and Fellow of the American Association for Advancement of Science in 2017. Today, Dr. Parry is going to give us the talk entitled Authentication and Obfuscation of Integrated Circuits. Please join me in welcoming with a strong applause to Dr. Keshav Parry. So, at the end of the presentation, you will have a list available for the certificate.
Thank you, Dr. Parry. Thank you for the very kind introduction. And it's a great pleasure for me to be here and give this talk. And this is the talk that is sponsored by the IEEE Circuits and Systems Society distinguished lecture program that allowed me to come here. So I can briefly say that Circuits and Systems Society is one of the 39 societies in IEEE, and being a member of the society has many benefits, including getting cheap registration for conferences and getting access to IEEE Circuits and Systems Society journals. So I would encourage particularly students to be involved in Circuits and Systems Society and be active in publishing papers in IEEE Symposium on Circuits and Systems, which is the annual meeting, and in publishing in IEEE Transactions on Circuits and Systems and other journals within the scope of society. Okay, so today my talk is going to be on hardware security. Security has been an important topic for a long time for software, and there has been a lot of research on software security. But about 10 years ago, this hardware security topic became very important, where it is important to secure the hardware circuits that we are designing, and we will look at how it is easy to reverse engineer circuits. And so that means people who are involved in piracy they can reverse engineer circuits and take away the secrets. And how do we design circuits that cannot be easily pirated? And we'll spend some time talking about that. So, so this slide shows some of the background for uh, the need for hardware security. So, shift of design challenges. And 10 years ago, we were always interested in area, speed, and power. But today, we have to be more aware of design for reliability and security. Globalization of integrated circuits. So if you think about a company, well, right here there is Clarify, Infi, and there is Infi in Irvine, there is Infi in Santa Clara, and that's an example of 3 different places. So there are designers designing chips, parts of the chips, not of the whole chip, but parts of the chip in 3 different parts. And now think about the design, a big design in Intel or Broadcom or whatever company you name it. They probably have people in 5 or 10 countries contributing to parts of the chips. So when we think about globalization of integrated circuits, what can happen is many things can happen. Many things can happen. People can insert hardware trojans, for example, where you take the chip and give it to foundry sends chips back, but we don't know, the designer doesn't know that there is a small circuit that is either actively or passively monitoring the chip. If it is passively monitoring the chip, then it's just monitoring the chip, maybe any current or voltage, and not doing very much. Maybe it's just transmitting passively to an attacker who is collecting information. If it is an active Trojan, well, it can modify the functionality of the circuit. Circuit is not functioning anymore as it was supposed to. So that's an example of active Trojan. Active Trojan is changing the functionality of the circuit. The passive Trojan is not changing the functionality, but monitoring the activity of the circuit and transmitting that information for the attacker to gather that information. And we don't know, the designer doesn't know, because let's say in some country X, some group that was designing this, some engineer inserted a Trojan into the Verilog board. And well, this is not, these things are happening. This is not imaginative things. These are happening a lot. Lost revenue and jobs due to counterfeit ICs. So let's say that, well, I mean, of course, many people have heard of counterfeit Rolls-Royce watch and all those things, but think about some company has a modem, as an example, and the modem, and another company has a counterfeit part. How can this happen? Well, think about a fabless company that designs the chips, sends it to foundry. Now, somebody sitting in the foundry produces 5 million extra chips. Okay, the company wanted 10 million parts. You send your mask, tell the foundry, send us 10 million parts, you pay for it. Now, some disgruntled employee in the foundry makes 5 million extra to black market, where they sell these parts at half the price or even 1/3 the price. Now what happens? Well, now somebody is selling the same part at half the price, and all the investment in dollars and billions of dollars in developing IP, developing the design is gone, because you can't sell your product because somebody is selling the same product for half the price. And that's because of excess production by the foundry. And we want to design chips so that the excess production by the foundry cannot happen. And even if somebody produces excess parts, the chip is not usable. So that's what is one aspect. So there are many aspects. So hardware security. So I say that loss of revenue and loss of jobs. If you lose revenue, you can't hire new engineers. Hardware security is critical to national defense. Obfuscation, this is what I'm going to talk about in the second part of the talk. Obfuscation is necessary for anti-counterfeit. So we'll talk about that. The design of integrated circuits that can be authenticated and obfuscated for systems with heterogeneous and complex hierarchies. So we'll talk about that as well. And this is one example from this paper here from Vyasanor and Teranipur in IEEE Spectrum from 2013. Recycled electronic products accounting for 80 to 90% of counterfeit parts in circulation by this 2010 estimate by this company in San Diego, Connecticut. So definitely there is tremendous need for design of hardware circuits so that they are secure. They are secure with respect to many criteria. They can be authenticated in a secure manner. They can be designed in a way that cannot be reverse engineered. They can be designed so that somebody cannot produce excess parts. And so those are all the objectives. So the two parts of the talk, one is authentication, and we'll talk about authentication, and we'll talk about functional obfuscation, and that can prevent reverse engineering, prevention of sale of excess parts, and we'll talk about two ideas in obfuscating circuits, the fixed and the dynamic obfuscation. Okay, so that's the outline of the talk. So the first part of the talk is I'm going to talk only about one small part here, so-called multiplexer physical unclonable function. So physical unclonable function called PUF, this term called PUF, which is physical unclonable function, that primarily is now an idea that is 20 years old. So when people started talking about PUFs, physical unclonable function, these are small circuits that cannot be cloned. Okay, so the idea is to generate random number generators and keys in a chip so that they are not stored in a memory. That's kind of the one of the ideas. So what exactly is a multiplexer physical unclonable function? So think about this. So we have this, let's say that we have 100 stages. So we have cascaded multiplexers. Okay, so there are control bits here, which we call challenge. And then there is an output, which is called a response. So what is basically the idea of authentication? When you go to an electronic banking process, maybe when you open your account, it will ask you what street you were born, what is your mother's maiden name, and you answer those things. It stays in the server. Next time you log in, it asks you same questions, and then you give answer and it checks. That's what is authentication. We are doing same thing here. We are not asking a question about what street you were born, or we are not asking about what's your first car, or where did you go to university. We are not asking those things. We are simply providing, instead of asking questions, we are providing a bit stream of ones and zeros. So that bit stream is the challenge. And the response, the answer that you store in the server, that's the response, 1 or 0 coming out of it. Everything is just bits of ones and zeros. So this challenge, if this was a 100-stage multiplexer physical unclonable function, we would have a challenge that is 100 bits long. So each bit, this bit here is challenge bit to this stage, and this bit, challenge bit, control bit to this stage. All together the 100 bits is one challenge. And after it goes through this whole circuit, we get one output bit, which is a 1-bit response. So let's say that I want to design a signature of this chip, and then let's say I want a 1000-bit signature. I want a signature that has 1000 bits of ones and zeros. And then I apply 1000 challenges. Each challenge is 100 bits. So I apply challenge, 100-bit challenge, once, twice, 1000 times. And after applying 1000 times, the same, in this circuit, we get 1000 bits, that becomes the response. And then we can authenticate the chip based on whether the response is correct or not. And we can usually tolerate a few bits error. We'll say, okay, well, out of the 1000-bit response, 996 bits are correct, That's still okay. That's still okay because it's only 4 bits and the circuit can have different functionalities because of environmental noise, temperature variation, and all kinds of things. So if we can say, okay, if the Hamming distance is less than 2 or 3%, so it is 1,000-bit response up to 20 or 30 bits can be wrong, and we can say, okay, it's still correct. It's the same chip. We can authenticate the chip. So what exactly is going on in creating that response? So this response 1 bit that is generated here, what does that mean? So it says that if we take this circuit and just employ a rising edge of the clock, so we have a signal that goes from 0 to 1, and it goes through all these 100 stages. Now if you look at what is going on in each stage, so if it so happens that this challenge bit will be available, yeah, let's say that if this challenge bit is 0, what happens when this challenge bit is 0? So if the challenge bit is 0, this path goes to the right of the output of the mouse, and this 0 means this goes to the right. If that control bit is 1, this part goes down and this part goes up. So the challenge bit controls whether these signals coming from the previous stage are going straight or swapped. So that's what the challenge bit controls. Now if you think about in each and every stage, I can have 2 possible paths. It can either go straight or it can go swapped. And if I have 100 stages, there exist 2 to the power of 100 possible paths for that clock edge to reach the end. So there can be 2 possible paths here, 2 possible paths here, 2 possible paths here. So there can be 2 to the power 100 paths, all possible paths. But once I fix this challenge, then this control, this rising edge of the clock will keep moving, sometimes straight, sometimes swapped. So it will keep moving, and sometimes, so this is an arbiter which is a latch, and sometimes the bottom output will reach after the it will reach before the top output. So this rising edge reaches the bottom output first, and that we say the response is 0. And in this case, if it so happens out of these 2 possible signals coming to the arbiter, if it so happens that the top input comes first and the bottom next, then the output is 1. So the output response is 0 or 1 depending on whether the top edge comes first, then it's 1, or the bottom edge comes first, that's 0. So that's what is the response. Okay, so we have talked about the challenge and we have talked about response. We have talked about generating signatures. How is it unique to chips? So these have to be unique to chips so we can authenticate. If I have 10 million parts, then I have to authenticate these 10 million parts, so every chip has to have a unique signature. So how do we guarantee these signatures are unique? Now, it so happens that if we take this small circuit, the physical unclonable function, and implement that in 10 million chips or any number of chips, we have the same design, same layout, everything is the same die, fabricated at same time in the foundry. But it so happens that there is enough variation in the foundry during manufacturing so that the process variations and leads to threshold voltage variations, and that leads to a difference in the propagation delay of this straight path and the swapped path. So at every stage, even though these designs are exactly same in the computer, they're sent to the foundry, when they are manufactured, the inherent small amount of process variations is enough to have variability in the difference in delay in each and every stage of this mux pop, so that the signature is unique to each design. So the uniqueness of the signature is due to the process and foundry variations. That's the important thing to understand. circuit design is same, the layout is same, everything is same, but there is variation in the threshold voltage that leads to the variation in the propagation delay, and that propagation delay leads to the uniqueness of these systems. So, so here is an equation for the total propagation delay. I won't go through that, and there is a paper that is cited here from Professor Devadas at MIT and published in this conference here. So it so happens, so what was thought to be unclonable when this paper was published, and for a long time it was thought, well, this is now every signature is unique. Yes, that's correct. Every signature is unique. Now, can this so-called physical unclonable function be cloned or attacked? Yes. People quickly figured out that it's very easy to attack this puff, because after all, if you think about this total propagation delay through this chip is expressed by some linear circuit, it's pretty easy to hack a linear function. Well, you can design anything to hack a linear function. So that's really not easily attackable. So it can easily be attacked. So so the goal of this research has been for a long time, how do we design these small so-called unclonable functions are really unclonable? And that means they cannot be modeled by software. And that means we can't clone, as in software, the behavior of the circuit. So the circuit that I showed here is, although the name says it is unclonable, is easily clonable. So how can we then have some nonlinearity? So there has been interest in employing nonlinearity, and the nonlinearity is introduced here. So I can say, okay, I am not going to take an external challenge bit to this multiplexer stage, but I am going to have an internal arbiter here, and that output now is a response. So that introduces some amount of nonlinearity. And this one shows, this is called a feed-forward pop, because this output here from the arbiter feeds forward to the multiplexer stage. This is called a modified feed-forward, which is taking the output here and feeding that to two consecutive stages. And it so happens that this has more reliability compared to the previous one. So the so-called modified feed-forward, but less secure, means can be easily attacked. Okay, so there is another paper there. So I already talked about this. So this is what the modeling attack is. So the modeling attack says that if I take the straight path and the swap path, both to be Gaussian variables, then the difference of the top path and bottom path is a Gaussian variable. If each of the path delay on the top and bottom is Gaussian variable with certain mean, and the difference of the mean will be 0, the same mean cancels out. And if the variance of each of these is sigma squared, variance of this difference is 2 sigma squared. So, but we won't get into that a lot. Let me just skip some of these slides. Okay, this shows how the response is computed. So after we compute the total path delay, which I showed in the previous slide, we take the sine function of that. If it is greater than 0, then that's response bit is 1, and if that is less than 0, then the response bit is 0, and that's how we model. We model the PUF in software by that process. Okay, so this is a chip that we fabricated at the university, and we sent it out, and it was fabricated by the IBM process, by IBM at Global Foundries at that time. So this is a 32-stage multiplexer, stage number 1 to 32. This is a feed-forward PUF where N1 is 16 and N2 is 26. That means we take the output of the 16th stage, feed that to an arbiter. That responds to the challenge bit to stage number 26. So this is stage number 26. And here this is modified feed-forward where that output is fed into 26 and 27. So that's kind of the chip. We collected a lot of data from the chip, and we tried to use all kinds of neural networks to train models for this data coming out of, not out of simulation, but out of the real measurements in the lab. So we are trying to see if we can learn the models for these pups. That's the intent, and that's, so there was a paper published in this ISL PET, International Symposium on Low Power Electronics and Design. So this is the 32 nanometer reconfigurable feed-forward puff. It is reconfigurable. That means each we have two control bits. Each the two control bits will configure the puff to be standard puff, or feed-forward puff, or modified feed-forward puff. So that's three possible configurations. And then the arbiter here is SR latch. Okay, so there is more detail in this paper, but let's see what it says next. So we get all the data, and then how do we really learn the model of this? So first of all, I have all the challenges and I have all the responses, and I'm interested in learning the model. So how many parameters are there in the model? So if I have a 32 stage physical unclonable function, I have this so-called delay difference that I showed delta I. So that delta I, so that is one per stage. So essentially in a 32 stage puff, we have 32 parameters, the delay difference parameters, and the arbiter delay, which is another term. So for the 32 stage puff, we really have 33 parameters. So this is the 33 parameters that we are trying to learn. 32 delay differences and a bias term of the arbiter, and we can express that as a linear function y equals w transpose x. And now it so happens that the student who worked on that, Mr. Avaru, and he tried to see, okay, let's use a least mean squared adaptive filter. And that's a filter that is well known adaptive filter structure. So if we feed these challenges as the input, and we have the LMS adaptive filter algorithm here operating, and I know the desired response. So I know the challenge, I know the response, and I want to learn these 33 parameters that are called weights. So that's what I am interested in learning. And it so happens that we could easily learn. We could easily learn the parameters using this. After convergence, you keep feeding maybe 10,000 or 2,000, whatever number of inputs, and then we know the response, we train the model, and then we test it on a new challenges. We keep that data secret, we don't use that data for training, and then we say, okay, now can we use these coefficients to predict the response? The answer is yes. So this is so once we learn the model parameters from the LMS adaptive filter, this is showing the delay difference of these 32 stages, from stage 1 to 2. And these are two physical unclonable function chips, PUF1 and PUF2. So what we see here, so for example, for PUF1, this is the estimated parameter for one PUF, another PUF. PUF2, these are two parameters. PUF32, stage 32, two parameters. Now, what we learn from here, it shows here that indeed these delay parameters are having mean 0. So we assumed that the delay parameters had mean 0 and variance some sigma squared. And if you look at these are random enough that we can think of these for both PUF1 and PUF2, they are Gaussian. And these are 0 mean, so these are all centered around. Now this slide shows, now each chip that we fabricated has 96 PUFs, 96 circuits. This is showing the estimated delay difference of 25th stage, stage number 25, coming out of 96 PUFs in the same chip. And that looks like Gaussian. So the Gaussian assumptions that we had made for simulation purposes are now verified from the measured data in the lab. So that kinds of is telling us that okay, these assumptions are correct. Okay, so now there is something called predicting hard response. I'll talk about hard response and soft response. So let me say what is soft response. So this particular chip is really a soft pop. What does soft pop mean? So well, pop has a response that's 1 or 0. What is soft pop? So what this chip does, it applies the same challenge 1000 to 2400, which is 100,000, about 100,000 times. So there are circuits in the chip that apply the same challenge. So there are these circuits, these odometer circuits, this silicon odometer. See, these circuits are applying, so no human is doing that, but the circuits are applying the same challenge these 100,000 times. And then, so if we apply the same challenge 100,000 times, in the ideal case, we would expect the response to be same all 100,000 times, but that's not really true. There is always some noise, some fluctuation, some small variation. So maybe let's say that out of 100,000 times, 93,000 times the response is 1. So we say that the probability that the response is 1 is 0.93, and that's what is called a soft response. So we are not just saying that the response is 1 or 0, we are saying the response is, let's say, 0.93. We know that the probability of 1 is 0.93, then that's likely 1. If the probability of 1 is 0.05, then that's likely 0. Now what about if the response is 0.6? Well, that's what we call an unstable challenge. That means even though I apply this 100,000 times, 60,000 times it is 1, 40,000 times it is 0. That means we should not use that as a challenge to authenticate the chip. So we should be using stable challenges. Stable challenges means we can design a threshold, whatever that you define. We are using 90-10. That means if the soft response of probability of 1 is more than 90%, that's 1. If it is less than 10%, it's 0. Otherwise, we just don't use it for authentication. We call that unstable challenge. The challenge is unstable. Okay, so now we are going to design machine learning models for learning the hard response and soft response. Okay, this says here that we are using a perceptron. So this is nothing but a perceptron. So these are the challenge bits x1 through xn. There is a bias term. The bias term is the arbiter delay. So now think about, this is exactly same as the linear model. So this is same as the linear model, so-called perceptron, and the activation function here is, if it is less than, it's the same as the sign function. If it is less than some value, some threshold, it's 0. Otherwise, it's 1. Okay. So using this perceptron for the standard arbiter pop, which is the standard pop, we can learn the hard response with about 98 to 100% probability with about 1,000 challenge response pairs. So if you keep running this, after about 1,000 challenge response pairs, we have learned the model, and the perceptron will tell us correctly what it is. And interestingly enough, the parameters that are come out of training a perceptron are linearly proportional to the parameters coming out of the least mean squared adaptive filter. Interesting. So, okay, and then for feed forward, so this is standard pop. For feed forward configurations, we need multi-layer perceptron with one hidden layer of 30 units. So that's for feed forward. These are all part of hard response. We'll talk about soft. And so let's see what this is here. This is for predicting soft responses defined based on 90-10 thresholding. Perceptrons for soft response. So if I take the same perceptron, I have a sigmoid function. Instead of the sine function, I have sigmoid. That can generate the soft response of the standard part. Okay, and we can see the accuracies are close to 100%. For feed forward configurations, this is feed forward pop. For a hard response, we have 30 neurons in this intermediate layer or the hidden layer using a sigmoid activation function. That's for hard pop. For soft pop, let me see the next slide. For predicting soft response, we need two hidden layers. One hidden layer with 30 neuron, one with 10 neuron. in any case, it is what it shows that even though we have introduced some nonlinearity and call it feed forward and modified feed forward, these can still be learned not by simple perceptron models or the linear models, but by neural networks, either using one hidden layer or two hidden layers. So we can learn the model. So the basic summary is these are still clonable. These are still clonable. Okay, so I'm going to skip a few slides. So then, okay, so these are more examples of feed-forward pop. We are now having two intermediate arbiters. So here it is showing that stage number 10, this is a 64-stage MUX. Stage number 10 goes to an arbiter. That output is an internal challenge to stage number 20. Stage number 15, there is another arbiter. This feeds to another arbiter whose output goes to stage 30. These are feed-forward pops with multiple intermediate arbiters as opposed to one that I talked about. So I'm going to skip a few of these slides because we may be taking a lot of time. But I think the main idea is that these feed-forward pops can be still learned, the model can be learned. So I'm not going to spend more time. There is a paper, in fact, that will be published tomorrow. No, this is in July. So how can we design these MUX pops that are really unclonable? And it so happens that a simple modification of the so-called XOR pop. So now we are talking about multiplexer pops which are based on XOR function. Exclusive OR is a non-linear function. Exclusive OR is not linear. So this paper that we published in Design Automation Conference, so we are going to see why this is unclonable. So now so we have the same pop, the same challenge is feeding, input challenge is same to all these n pops. Now n pops are generating n binary responses. These are binary. Then we take the exclusive OR, that's the final response. That's the idea of XOR pop. So if I want an XOR pop with 10 components, I have 10 pops, I feed same challenge to all 10, I get the response from all 10 and take the exclusive OR, and that's final response. And why is this unclonable? This is unclonable because the attacker needs access to all these intermediate responses, but the attacker doesn't know what these are. The attacker simply knows the final response coming out of the chip. If the attacker had access to all these intermediate responses, the attacker would be able to model all these individual components. But now, because of the exclusive OR output, the attacker does not have access. These are invisible, so therefore the attacker cannot easily model the exclusive OR pop. Okay, so let's see this plot here. This plot shows the number of training set size challenge response pairs such that we can get this prediction accuracy. This says if the pop had 4 components, n is 4, I can get 100% accuracy. So that means an exclusive OR pop with 4 components is easily clonable. If I go to n is equal to 9, then I can get 92% prediction accuracy, still clonable. If I go to n equal to 10, I get 86% accuracy and still clonable. So using about 1 million challenge response pairs and using this neural network, we are able to clone this XOR pop also. So the XOR pop can also be trained using neural networks. But if it is more than 10, then we can no longer predict. The response becomes about 50%. And that means the XOR pop is not predictable if we have more than 10 components. Then it's not predictable. You take very long time for the neural networks, then they don't converge and you cannot train them. Okay, so now we say, okay, well that's good. Now what happens if we take the same XOR pop? This actually will be presented tomorrow at the Great Lake Symposium. So now we take this XOR pop everything is same, POP, these are L components, POP1 through POP-L, but each of these components now is not a linear POP, but a feed-forward POP. So we are using a feed-forward arbiter POP as components to these XOR POPs. So in the previous paper that I talked about, these were all standard or linear POPs, and now these are non-linear components. So, so what it shows here, if we take these non-linear components, and this is already training these with artificial neural networks with 3 hidden layers, 120 neurons in one hidden layer, first hidden layer 30 neurons in second and 15 in third, and that's already a very large neural network. And it shows here that if I have 5 components in the feed-forward XOR POP, I can get accuracy of 75%. But if I have 6, 7, and 8, any number greater than 5, so in the standard XOR POP, we have to exceed the number of POPs to be more than 10. If I now make the component POPs non-linear, then as long as I have now more than 5 components, 6, 7, and 8, then the prediction accuracy is 50%. And that's like flipping a coin. So that is not predictable or clonable. So that's kind of the main observation that we get from this slide. I probably can skip a few more and go to, okay, let's see here. So this slide shows reliability and security. I won't go into the details, but there is a lot of result here using multiple feed for multiple arbiters. So for example, this is 4 different arbiters. Arbiter at stage 15 going to 55 and 56. So the internal challenge at these locations are coming out of 15. Internal challenges at 50 and 51, the stages come out of an arbiter 20. So these are many arbiters, many feed-forward paths, and the summary, I suppose, if you look at the last column, using soft thresholding that I talked about, these reliabilities are still pretty high, more than 92%. So these, we have to make sure they're reliable. So these are reliable, these cannot be cloned. So I think the summary is using XOR POP and nonlinear components, we can get access to feed-forward XOR POPs that are reliable and secure. Okay, so there is quite a bit. Okay, so feed-forward XOR POPs cannot be accurately modeled if the number of component POPs is more than 5. Reliability decreases as more components are used. However, we can increase the reliability by modified feed-forward structures and by the soft thresholding idea that I talked about. Okay, so that kind of completes the first part of the talk where we are interested in authenticating devices using these unclonable functions. I'm going to switch topic to the obfuscation, where we want to prevent sale of excess parts and reverse engineering and intellectual theft, by intellectual piracy theft. So that's the idea is to functionally encrypt the chips during design process, so that even if somebody has 5 million extra chips, they can't use those extra parts because they don't know the key. Each time I functionally encrypt the design, I introduce a key, and somebody who has the chip but without the key, they can't really use the chip. So that's the idea of the next part. Reverse engineering is feasible when the adversary gains access to the device. No static definition of secure. How much does it cost? As long as there is going to be profit, so the attacker is interested in profit. I mean, that's what. As long as the attacker can make profit out of either selling the parts at half the price or whatever, or sometimes what they are doing is sometimes, for example, if you look at old equipment, it could be an old aeroplane or it could be simply an old equipment, and it so happens that the part is no longer available. So let's say we have an equipment that was manufactured 20 years ago, and there is a part that is now not functioning correctly, and that part is no longer sold by the original manufacturer. Maybe the original manufacturer has closed down, and so what do you do? Well, okay, we can say, okay, we need another part, that meets the same spec, and I can then put that part where the part has failed. If it's on the board, I can then replace that part. What companies are doing, they are taking these old parts, they have access to old parts, and they are taking the package out, they're putting new package, and they're selling that as a new part, and for a very high profit. And that's going on quite a lot. So that's what is called counterfeit parts. So companies are doing that. I mean, they just take the package out and repackage and call it new part. So now here is the problem. Somebody sells you something and says this is a new part, and you expect this to last 10 years or whatever, and lo and behold, you don't know that this is already a 10-year-old part or maybe an 8-year-old part, and it fails in 2 or 3 years. So that's kind of what is happening. And in fact, there was this study, there was this aeroplane with a wrong part, which was an old part like this, with a new package, and the part failed during the flight. And so in such a case, the plane can crash, and that can happen. And it's so these are things that those are the motivations for hardware obfuscation. Hardware obfuscation is a technique in which the description or the structure of the electronic hardware is modified to intentionally conceal its functionality, which makes it significantly more difficult to reverse engineer. It affects the human readability of the source code, encrypts the normal functionality with a secret key. So these are some examples of DSP parts: FIR filter, turbo codec, modulator, correlator, and many of these are familiar blocks in signal processing. DCT, discrete cosine transform, MPEG. So these are all. So DSP is a big technology, is an important technology in all these applications like video compression, portable computers, multimedia, wireless communication, suites, biomedical. So, so there is definitely a lot of interest in designing DSP circuits that cannot be reverse engineered easily. So, typically in the design process, so this is the foundry, we call Alice. Alice is sending something to Bob. So the foundry, this is the design house. Think of this as Clarify or Broadcom or whoever. So they send it to foundry, and the foundry manufactures the chips. And now the design house has many vendors, many IP vendors. So instead of sending this to the foundry directly, what the design house does, so it includes a secret key, and that secret key is embedded into the design. So IPs are coming from different vendors. The design house integrates the design with a secret key and then sends to the foundry. Now the foundry has fabricated all the chips. Now the design house gets all these parts back, and then they send it to some other company. And they tell, here are the keys, you program it. So the foundry does not know the key. Some other company, some customer company, or maybe the design house itself, if they have the ability, somebody else gets these parts from the foundry, and the design house gives the secret keys. The foundry gives the chips, design house gives the keys. These keys are programmed into the devices, then that goes out to the marketplace, to the end user. So that's the process of encrypting chips in a functional manner. So we are going to talk about how to introduce these keys to encrypt the designs so that somebody else with 5 billion extra parts cannot use these chips because they don't know the key. So we are going to talk about that. Okay, so this is the same thing we are talking about. Globalized semiconductor manufacturing supply chain leads to IP piracy, integrated circuit overbuilding, reverse engineering. People can look at your chip under the microscope and reverse engineer what you are doing, and that's happening every day. companies want to know the competitor secrets. Company X wants to know how many taps are in the adaptive equalizer in company B's product, or company, and they put it under microscope. I won't name any companies, but I know that the companies have done it, and we will not name any companies here. But companies are doing it, and I am aware of companies doing that. And some company wants to know what is the effective size of the competing company's product. And so we want to protect these parameters. And that means we want to prevent reverse engineering, because if the company can find out those key parameters of our design, they can then replicate what we are doing. And we don't want our competitors to know those parameters. So those are all objective. Huge loss in revenue for the manufacturing industry. Countermeasures, there are many ways you can encrypt these. I'm going to talk about functional obfuscation, but there are logic encryption is one, isometering, fingerprinting. Okay, so there are many other methods. There are some papers listed here, proceedings of IEEE. So this is the starting point of a two-level finite state machine. So think about a two-step authentication, two-step functional encryption. So we have a key that is L plus K bits. So this is an L bit key and this is a K bit key. And we will call that the initialization key and configure key, but we'll talk about that. So what does this initialization key do? So the initialization key is saying that if your initial L bits are wrong, you can't even access the chip. The chip even won't turn on. We want to trigger the chip. So that's kind of what the initialization key does. So here is an example of an initialization key. So let's say that the initialization key, the correct key is P0, P1, P2. So if this is a finite state machine, I'm starting in the starting state as 0. You input the key bits, P0 goes to S1, P1 goes to S2, and P2, it then activates the actual parts of the circuit. So this is not even part of the circuit. This is just an initial step where we can, if the initialization key is correct, then the circuit becomes activated. And then the K-bit key, which is the key here, will configure the circuit, and if the K-bit is correct, the circuit is going to compute correctly. If the K-bits are wrong, circuit will still compute something, but it's going to be computing garbage. So that's the idea, it will compute garbage. So this is the block diagram. We start with the key, the configuration key, then this reconfigurator has these control signals. So we'll see what the details are. Okay, so if the P0, P1, P2 are wrong, then the circuit doesn't even activate. If it activates, then we'll see that it will compute something. So the idea here is if the initial key is correct, then we depending on the other key, we can have desired designs or garbage computations. If the initialization key is wrong, if the initialization, if the initial design is, initial key is correct, configure key is correct, then it's functioning as desired. If this key is correct, configure key is wrong, it's computing garbage. If the initial key is wrong, then you try a few times. Let's say we set a maximum threshold of 10 times. You try 10 times, then we have denial of access and denial of use, and it just doesn't allow. So it creates an alarm mode. So you can't use it after 10 attempts. You can't even use it anymore. So that's exactly what your bank does. If you put password wrong 4 or 5 times, then you can't log on. Maybe you either go to the bank to reset or you wait. Sometimes they will let you log on after a time period of 1 day or 2 hours or whatever. So So there are a couple of papers here, well, at least this is the first paper published in Transactions in VLSI Systems in 2015, and there is another paper. So we are going to talk about what these things mean, meaningful mode and non-meaningful mode. So what does it mean to have meaningful mode and non-meaningful mode? So the meaningful mode means circuit is computing correctly. Non-meaningful mode means circuit is computing something, but it's not computing what it should compute, it's computing garbage. And I'm going to illustrate the idea of encrypting by using a fast Fourier transform architecture as the target design. So we are going to use the FFT, and we want to encrypt the FFT so that the circuit cannot be used unless the key is correct. So this, we won't get into detail. There is, in fact, this is published in 2015 from signal flow graph of the fast Fourier transform, and we can design using folding an architecture that has this delay switch delay, butterfly phase, this is a 2 parallel FFT, and that has all these delay switch delay and butterfly stages. And some of you who are working on FFT or who are sitting in my class this week, we have gone through this in the class. Okay, so in this FFT, there are a number of multiplexers. So for example, in this butterfly 1 is fine, butterfly 1 is, so this is taking the, this is computing x1 plus x2, x1 minus x2, it's computing real and imaginary parts. Now, this butterfly 2 has a control bit T. Okay, there's a control bit T. And that control bit is input to this multiplexer. And if the control bit is 1, then x2r goes to output, x2i goes to output. If this control bit is 0, x2r goes to bottom, x2i goes to bottom. So what it means is, depending on whether this control bit is 1 or 0, this real part and imaginary part of x2 go straight or swap. And why would we want it to swap? A lot of times there is a twiddle factor with minus j. That means the x2 real part multiplied by j becomes the imaginary part, and the imaginary part multiplied by j becomes real part, and that's how we swap these real and imaginary parts. So if there is no twiddle factor minus j, this goes straight. If there is j, then they swap. So that's the purpose of that control bit. There is also delay switch delay, that's these 4 delay switch delay, 2 delay switch delay, and so on. So in these delay switch delay, there are these multiplexers here. So for example, this is n delay switch delay, there are n delays here, n delays here, and there is this mux, 2 muxes with the same control signal. The same control signal S is feeding to both multiplexers, and that's again same thing. Either these inputs here are going straight or they are swapped. They're swapped, this path goes up, this path goes down, or they go straight. So that's what that's doing. Same thing as the other ones. Now these control bits are available to us to encrypt the chip. And how do we take advantage of encrypting the chip using these control bits S and T? Well, we will see how we can take that S and T. We can simply change these control bit patterns to create garbage computations. And how do we create garbage computations? Well, this is a correct functionality of this delay switch delay. So there is one delay and mux and delay, and if these are the inputs, these are the outputs, this is correct. Now, if this works correctly, if the control sequence to this multiplexer is alternating zeros and ones, if I have 0, 1, 0, 1, 0, 1, then the circuit works correctly. Now, if I change this to all zeros, then half of these red points are wrong. If I change this to all ones, these are wrong and skewed. These are skewed in computations. So the idea is I can use keys to garble these control, the control bits. So that's what we are trying to do. How do we garble them? Okay, well, we will use keys to that. So that was using this control signal S for the delay switch relay. If I have the control signal P for the butterfly, same thing. If I can change this alternating zeros and ones, I change it to all zeros. So this part, half of the outputs are wrong. So the boxes are correct, the red ones are wrong. How are we going to obfuscate? By changing the control bits. So use control flow modifications to create correct or incorrect modes in the design. Trigger incorrect modes for incorrect keys, but only a small duration of time. So there are a few ideas here. Okay, so probably I have a, okay, let's go through this diagram first, then we'll talk about the previous diagram. So the so-called fixed obfuscation, that is saying that if I have a key bit K0 and key bit K1 and the control bit S, S1 and S2 are going to be correct control bits. So in this case the key for the correct functioning of this circuit, the correct key should be 0, 1. K0 should be 0, that means S1 should be C1, K should be K1 should be 1, so that's 1, that means S2 should be C2. And if this is wrong, that means this is 1, then this is C1 prime. And if this is wrong, that means K is 0, this is C2 prime. So you can see out of the 4 possible cases, we have correct key. If the key bit is correct, 0, 1, then we get the correct control signals, C1, C2, otherwise we get wrong ones. So that's what is called a fixed obfuscation. So fixed obfuscation says that if the key bits are correct, then the control bits are correct, and the circuit is working correctly, otherwise it's working incorrectly. Now there are two drawbacks. So the fixed obfuscation was the first paper that we published in VLSI transactions, but there are two drawbacks. The first drawback, somebody having access to the device, the person can sit down for a week and it doesn't matter, the person can sit down for a week and or maybe a day and then quickly figure out what the keys are. So, it's a circuit is operating at 100 megahertz clock, let's say, and each attempt is 10 nanoseconds. You can sit down, if it takes 10 million attempts, okay, that's not a long time, 10 million attempts times 10 nanoseconds, you can do that in a couple of days. So fixed obfuscation is a fast start, but then how do we design circuits that can, so when we design this, we want to design so that somebody cannot figure out the key in maybe 5 years or 10 years. That's the intent. I mean, the lifetime of a chip is about 5 years, and if it takes 5 years for the person to figure out the key, then that's a good design. So we want designs where the time to attack is exponential with respect to number of key bits. And in the fixed obfuscation, it's really not exponential, it's a constant. So that's the drawback of the fixed obfuscation. So then we said, okay, well, that's great, but then how can we use this so-called time varying obfuscation? So the idea of time varying obfuscation means that, it so happens, it's not fixed. That means even if the key bits are correct, circuit is computing correctly. But if the key bits are wrong, it is still computing correctly sometimes. And that means the attacker gets the correct outputs. Attacker may think that attacker found the correct keys, but the attacker may not really have found the correct keys, because even if the keys are wrong, it's still computing correctly. And that's time varying obfuscation. What does that mean? That says instead of, if the key bit is wrong, instead of having the wrong control bit as C1 prime, I can have this as some function of C1 and a trigger signal T1. So if the trigger signal is 0, then it's C1, so that's still computing correctly. Now if the trigger signal is 1, then this will become C1 prime and then compute wrongly. So now I'm using a trigger signal to control when it will compute correctly and when it will not. But what we found is that the lower bound on time to attack, which was constant in fixed obfuscation, is now linearly proportional to the number of bits in the key. So that's still good, but it's not as great as it should be. And then that led to the so-called dynamic obfuscation. So now we are not only using a trigger signal, we are also using a random number generator. And then we can say, okay, if the value of the random number generator is the same as the trigger signal T1, then garble the computer, so make it C1 prime, otherwise it will compute correctly. And that means that we cannot predict. So the circuit is now, well, at least in the time varying case, this behavior here can still be predicted in linear time and key. But here, because of the random number generator, we don't know what the random number output is. So the minimum time to attack is now exponential with respect to the size of the key. So that's what we are saying here. Time varying obfuscation, trigger incorrect. So control flow modification to create correct incorrect modes. Trigger incorrect modes for incorrect keys, but only for a small duration of time. Use concepts from hardware Trojan. So we are this whole idea of using trigger and using random number generator is really coming from this whole field of hardware Trojans, which by itself is well established and well researched field in last 15 years or so. So that's this paper in Transactions on Information Forensics and Security. So here is finally the example of how we obfuscate the FFT architecture that I talked about. So we have this. So this is the counter of the FFT. The counter of the FFT, and we are generating those control signals S and T from the using random logic from these counter bits. So now, let's say that I am mapping the key bit number 0 and 1 to this multiplexer. So what it is showing here is the so-called S0, which is the multiplexer control signal. The correct signal here, let's see, the correct signal is 0. If this is 0, I guess that should be the control, the counter bit number 8 is the correct signal. So now I have some garbling modes here. So if you look at what is going on in the second one, so that's the inverted control bit number 8. So counter bit number 8 inverted. If you look at what is going on here, and so what is going on here? Well, this is the AND gate of counter bit 9 and its complement, and that's always 0. That's always 0. Take the counter bit, counter 9, C and AND with C bar, that's always 0, and invert that, that's always 1. So depending on these key bits, I can now generate these. I can force this to be always 0, force this to be always 1, and force this to be something else. So that's how we map the external key bits to this FFT circuit. So if the keys are wrong, then these control signals are still generating something, but instead of say alternating 0 and 1, this could be 3 zeros and 5 ones, and something like that. So they will be computing garbage. So that's how the key bits are mapped to garble the modes by garbling the control bits to those multiplexers called S and T. So anytime we have a sequential circuit and we have a counter or something else, we can use those bits and some random logic to garble the control flow. And if I want a circuit with a million different garbage modes, well, I can do that. A million is about 2 to the power 20, and I can have 20-bit key, and if this key is correct, then okay, it's working correctly, and if the key is wrong, it's still computing something, but it's computing patterns. So this is showing the modified control signals for these switches, and by introducing these red parts, the red parts that didn't exist initially, and these design at design time, we are now encrypting the circuit so that somebody without the key cannot use this chip. So during Verilog design, you modify the Verilog code to encrypt the design. So this is showing the time to attack can be, this is 1 million years for a key size of 32 bits, that many cycles using 100 megahertz clock, that's 10 nanosecond clock period, that many cycles is equivalent to 1 million years. For fixed obfuscation, that's 21 seconds. So if somebody has access to this device operating at a clock speed of 100 megahertz, somebody can learn the keys by brute force in 20 seconds. Well, that's kind of not secure. That says it's not secure. The area and power overheads are not a lot, and that's because we are not changing the data path of the circuit. Data path stays intact. The control part is only changing slightly by some small number of random logic. We are reusing the counters in this system, so that's why the area and power overhead are not a lot. So this shows how the area and power overhead change with the key size. So if I let's say overhead of transmit module of Ethernet IP core. So so this is a standard standard chip, the so-called Ethernet IP core, and we took the Verilog code from the website, and I think somebody showed me downstairs this Ethernet IP core in one of the labs today. So this shows that using key size of 32. What is this MOX size? The MOX size 4 to 1. So that means I'm mapping 4 to 1 MOX. That means we have 4 possible inputs to the multiplexer. So that's an example of the 4. That means 2 key bits are mapped to each MOX. So anyway, that shows the time to attack. So in summary, the static obfuscation control signals are modified. Lower bound on time to attack is 1. Long keys need to be stored. Overhead is due to multiplexers. Only time varying control signals are corrupted with trigger signals. Lower bound is proportional to key size k. Smaller keys can be used. Overhead is due to additional trigger circuits. Here control signals are corrupted with randomized trigger signals. Lower bound is exponential in key bit size. Smaller keys can be used. Overhead is due to trigger circuits and random number selectors. So large modules can be obfuscated at several levels. Keys used at each level are only known to design house. So I didn't talk about this, but this is kind of the idea of hierarchical obfuscation. So what hierarchical obfuscation means, let's say that design group sitting here in Cordova designs a part and encrypts the parts just like I showed using say 10 key bits. And another group sitting in another place also introduces 10 more key bits. Now both of these vendors send it to a designer who now knows the 20-bit key. We don't here know what the 10-bit key is of the other group, but the designer knows our 20 bits and introduces new 10 bits or new 5 bits, and then it sends out to the foundry. So that whole idea of hierarchical obfuscation, people at lower levels don't know the keys introduced by designers at higher levels. So many vendors working in different places are providing in a hierarchical manner, and the chip can be encrypted hierarchically. So these designers themselves cannot really encrypt. Even if the designers got access to the chip, they don't know the key because they only know what key they used. If somebody at a higher level knows what keys were provided to that higher level, but may not know to the top levels. So somebody sitting at the very top level knows all the keys and introduces new keys. So that's what we are saying. The keys used at each level are only known to the design house or IP vendor at higher levels. It is unknown to other IP vendors at same level. Even though the overheads due to meaningful modes, they increase design complexity. Okay, I would have to explain more, but that's kind of, we'll skip that part. So linear and non-linear POPs can be modeled easily. Models can be stored in server instead of challenge response phase. So what we are saying here is that when you go to the bank and you store these, say give these answers, the server, the bank, stores the question and answer. So here we are saying that we don't really need to store thousands of challenge response pairs, but instead we can store these models. So if I have 100 stage pop and maybe one output arbiter and 10 internal arbiters, I can store 111 parameters as opposed to many thousands of challenge response pairs. So that's what that it's saying. New pop circuits that are attack resistant need to be developed, and I give one example. Control flow modifications can obfuscate circuits to design chips that are harder to reverse engineer. In addition, key-based obfuscation can render access paths unusable. So this is really, I didn't talk about this, but that's kind of what this sentence is saying. So this sentence, I didn't talk about it a lot, but this is saying that I can design an FFT circuit and somebody can look at it under the microscope, but the person won't know if it's a 256-point FFT or 1024-point FFT. The person won't know. Okay, what does that mean? That means the whole encrypting the chip that I talked about if the keys are correct, the circuit is computing correctly, and otherwise it's computing incorrectly. Now I can say, okay, well, I can say that the circuit can have multiple correct computations. So the circuit can operate as a 256-point FFT and a 1024-point FFT meaningfully for two different key combinations. And that's really what I didn't expand on that idea a lot. So for example, if you see these control signals, so if this control signal is 0, that would be the correct computation for 1024-point FFT. If this is 2, then it's correct computation for 256 point. And similarly here, if it is 0, it's computed correctly. So that means instead of defining, say, okay, that's the correct computation. I can have a configurable circuit that can be configured to many meaningful modes. They are still computing garbage otherwise, but so for different meaningful modes, we could have 256 point or 1024 point as two meaningful modes. With two different keys, they will be working correctly. So that's that idea, and that's really, so even though, so there can be multiple meaningful modes, so even though, and there is going to be a larger overhead, even though the overhead due to meaningful modes, the increased design complexity with increasing number of IPs, making it more secure. So if you can have multiple meaningful modes, and why is that? Well, again, the attacker may find everything is working beautifully with 1024-point FFT and may incorrectly conclude that's what our computer is doing. And that's kind of the purpose of embedding multiple meaningful modes to confuse the attacker what the real meaningful mode is. Okay, so there are, this whole thing was sponsored by the National Science Foundation Semiconductor Research Corporation. And there are a number of people, my colleague, Professor Kim, who designed, his students designed many chips, and a lot of students. Professor Rao finished his PhD, now Professor at Clemson. Sandhya has finished and is at IBM, Watson Research Center. This person has done Max Linear, and this person has done Intel. So we have a lot of good students working on these projects for about 6-7 years. So, okay, so I guess that is the end of my talk. And, questions?
The kids can use the chip for like a software for beginner, professional. It's for use same chip for many functionality, only variation the key.
You are talking about the second part, the functional encryption.
Yeah.
Okay. So say that again. There are many. There can be 2 or 3 meaningful modes.
The same chip for various functionality.
Yes.
Nodes, modes.
Yes.
Only vary the key for the
Only
different
vary the
functionality.
key. Yes. Only vary the key. Yes. Indeed. Only vary the key. Indeed. And so we have published some papers that talk more about those ideas. So I can say how. So for example, so the student who worked on this, she designed a circuit that can be configured as 256.FFT and 1024.FFT. So 1024.FFT has 10 stages. 256 point has 8 stages. So the first 2 stages don't even activate if it is 256 point. If it is 1024 point, then all stages activate. So there is a bit of control, and that's why the overhead is more when we have more meaningful modes. But yes, the student designed this configurable FFT which is encrypted. But yeah, that's I think that's the basic idea. So and indeed maybe sometimes it's not to confuse the attacker. We ourselves may be interested in having multiple meaningful modes. So in wireless systems, if the channel conditions are great, you may use 64 QAM. If the channel conditions are not so good, you may go down to 16 QAM, for example. So we may genuinely be interested in having our circuit configurable, depending on the channel conditions. And so this is not just to attack not just to confuse the adversary, but we may simply be interested in a configurable design, in which we are. We are often interested in configurable design.
Professor, one question. Regarding to the second part of the talk, obfuscation, what are the challenges for the researchers? For example, to reduce the area and power is also a challenge for that area. Or I saw 15% of increase in power and area, but maybe high some application.
Yes. So yes, I think that is true. So indeed, the area and power overhead can be large sometimes. So if you look at key size of 32, area overhead 55%, power overhead 46%. So definitely these can be quite large. But what we gain is the number of cycles it takes from time to attack, 2 billion cycles to 3 times 10 to the power 20 cycles. So, I mean, I guess this particular example is this Ethernet IP core, and this is, if you go to websites, you can find Xperillo code. This is quite a complex block. So, I must say that I don't know any detail of that block. The student figured that out. So yes, I mean, in the FFT case, we are able to easily garble the modes by changing the control bit patterns, and that's really not hard. So I should say that this was the first paper of its kind to introduce functional encryption. First paper of its kind, both fixed and dynamic. Definitely, this is the first work on encrypting DSP chips. But I guess the question is, what are new research domains in this domain of functional encryption? So I can see a lot of new domains for using these functional encryption ideas. I don't know if you have heard of something called split manufacturing. So there is this term, this whole research field called split manufacturing, and that means if we want to fabricate a chip, we don't want to send it to one foundry. we want to send it to 2 foundries. And so we send it to, first we send it to an untrusted foundry which can create all the fabrication of the lower level layers. All the lower, there are 7 or 8 layers in the fabrication process. The first untrusted foundry, which is cheap, that's a cheap process. And that can fabricate the so-called lower layers. Then that foundry sends the chips back, they are not complete, and then we send it to another foundry that completes the upper layers. The upper layers are more expensive. Now we send it to a trusted foundry which is more expensive. And this whole idea of functional encryption I suggested can be adapted to, if you think about these keys, the keys are no longer thought of as keys but as wires coming out of the first foundry and going to the second foundry. So these are wires going, and I can encrypt these wires. These are some correct wires, and I can introduce wrong wires. And so in a split manufacturing process, the functional encryption idea can be embedded into that in the split manufacturing process. And there is a lot of research going on, and I should say that, of course, is everything here useful? We don't know. I mean, at least I'm told by companies like Broadcom, or they tell me that this reverse engineering, piracy, sale of excess parts is not a problem for them. They say that they have not suffered. But of course, with the fundamental research is not caring about whether somebody is suffering or not. Fundamental research is bothered about what would happen if somebody did that. So the split manufacturing is again something like that. Is there a real need for 2 foundries and one untrusted foundry, one trusted foundry? I don't really know. I don't think that's a real problem today, but the research community is invested in that. And this functional encryption could be one possible approach to split manufacturing. I see that as a direct application. Okay, we have a question there.
Yes, when you show in one slide that the signer gives to the customer the key
Yes.
to make the proper
Yes.
function.
Yes.
So it's also possible to encrypt that key, right?
It's the same key. It's the same key that was introduced during the design.
Yes, I mean to give the key encrypt, so the distance between the correct key and slightly different key is almost another key, you know. So because, for example, in the case you showed,
Yeah.
when one bit change, the
Yeah.
functionalities are maybe close to the one desired.
Okay, I mean now you are talking about, yes, I mean you are talking about, well, I mean you are saying some of the outputs may be correct and some may be wrong. I mean that's what you are saying. Is that what you are saying?
I want to ask you, if I have the correct key,
Yes.
and I change one bit,
Yes.
maybe the correct functionality is slightly, so it's more easy to learn if it's not encrypted, the key itself.
Well, I mean, I guess I should say that. I mean, I think, okay, you are saying if you see, let's say that in the 1024-point FFT computation, let's say some 1,000 samples are correct, some 20 samples are wrong. And that means you can backtrack and say, okay, the key for this particular case may be wrong. Is that what you are saying?
Yes, yes.
Okay, okay, so that is why this dynamic obfuscation is really important. I mean, the dynamic obfuscation is saying that you can't really, the circuit, even if the output is correct, you are no longer sure what the correct keys are. So maybe the 1,000 outputs are correct, and that could happen.
Yes, yes.
Even if the key bits are wrong, that could happen. But I can see that what you are asking is an interesting research problem in itself. In this simple FFT example, can I figure out the effect of mistaken keys in the output and what part is creating faults or errors in what parts?
Yes.
And that in itself is interesting, and this would be very interesting. And those of you who have worked on FFT flow graphs will see that if I change, so if I have some input, I'm computing FFT, and I change one of the inputs, and that can propagate to numerous outputs. I think that's like n by 2. So each input change will affect half the outputs, n by 2. So I do feel there is interest, yes. I certainly feel there is some interest in learning what part is affecting what, and there is interest in that. There is definitely, FFT is a fascinating topic, and I've been myself fascinated. That's kept me busy for a long time. So there is definitely interest in learning these things.
Yes. Which thing is used typically in the chip? Ops or case, or authentication or obfuscation, or both at the same time?
Yeah, the authentication is used in many applications today. So a lot of real products today use POPs, particularly in RFID applications. So I don't think anybody is using obfuscation today. This is pure research. Nobody is using this now in real products. But POP is used in real products today to authenticate devices, whether it is RFID or some sensors. So that's used today. Yeah.
So, rather basic question about dynamic obfuscation. You mentioned that in this case you introduce a random generator, but I don't fully understand how is the key related with the sequence of this random number generator. You generate a different seed, or
yeah, that is a very good question. That is really an important question, and there is obviously a lot of details that I didn't talk about. How does the random number generator and the key, I mean, what I'm showing here is a fixed obfuscation, and we are not showing the modifications for. So there is a lot of detail in this paper, published in January 2018. But I can say that so even in the next slide, I didn't really show the trigger itself. So there is a trigger. What is a trigger? A trigger is like a Trojan. I mean, it's an aperiodic rare event. So we generate a circuit that generates a trigger. We design a circuit that generates a trigger, and then we have a random number generator. And we say that if the random number generator say is equal to the trigger output, so there is an if then else statement, and depending on the trigger and the random number generator, we decide when the key will be garbled and when the control bit will be garbled and when it will be not. So that paper gives all these details. It gives several other counters and circuits to show how the random number generator and the trigger interact. And so there is quite a bit of detail that I didn't talk about. But definitely that's yeah, if one needs to understand more detail, we need to look at the paper. Yeah.
One other one, more than managed question. So how do you point your research? Are you pointing your research towards 5G and, for example, massification of devices and embedded into ZigBee and wireless protocols, low power, something like that?
No, I am not working on any of those, unfortunately not. I mean,
because what you're saying is, I mean, it's quite interesting if you think of security as
Yes,
IPv6 applications and everything.
absolutely. No, absolutely.
Interesting application.
No, I think what he's saying is very important, and there is tremendous interest in wireless security. And the question is, can these ideas be incorporated into wireless security protocols? I have not thought about that. I really haven't spent time, but I expect in some way or other we should think about those ideas, and somebody, I suppose, may. But that is definitely, there is definitely interest in wireless security. There is great interest. And how some of these ideas could play into that, well, that by itself could be what we research. Certainly there is a lot of interest in security research today in many domains, not just hardware security, wireless security. There is interest in, well, in the computer architecture community. There is tremendous interest in firmware security. This Spectre meltdown, some of you may have heard of that, which is due to attacking the cache. So people are interested in preventing side channel attacks on the cache memory. And there is interest in that as well. So there is tremendous interest in companies like Intel and AMD and Google and Apple. All of those companies are much invested into that research. Thank you very much. It's a pleasure to be here.